Okay, thank you very much. So it's a pleasure to be back here at Saclay for a couple of days. And thank you to the organizers to allow me to present our work here. So what I'm going to discuss today is a new family and a new kind of approach of the quantum many-body problem. And I thought, so it's changed slightly my title, but the content is the same. I thought it's a good thing for this conference because basically what it is merging two ideas. One of a famous paper by Cyrano, where he's done multiple Legendre transform to compute higher and higher irreducibility functional for the quantum many-body problem. It's famous paper in '64 with Martin. And the second idea is the fact that you can do atomic approximation on the irreducible part of these objects, which started with first of this method, the dynamical mean field theory, or DMFT. So basically what I'm going to present is a new method that combines these two ideas. And this work started a couple of years ago by a discussion with Cyrano here about this paper, about how we could combine them, how we could understand these ideas. So my outline is quite simple. First, I'm going to explain a little bit, what kind of problem I'm interested in and what is a quantum embedded method. Then I will present the formalism basically first on DMFT because it's simpler. That's the first method of this category, and then I'll be able to generalize and present what I really want to present, meaning the Trilex method, and I will explain later what Trilex means. So let me acknowledge my collaborator. A large part of this has been the PhD of my former student Thomas Herald here in Saclay, and a lot of work has been done also with my postdoc, Yaksha Vucicevic. Now, of course, working with new people, both here and in New York. So the problem I'm interested in is a quantum many-body problem. So just to start simple, for example, electrons in a solid. Well, we know how to write an Hamiltonian for electrons in a solid. I write here a simple version without spin orbit, for example, but you have the electron interact with the crystal, the potential created by the crystal, and they also interact together with the Coulomb interaction term. Okay? We know it's important because it describes most properties and electronic property of a material, conductivity, optic properties, magnetism, also the structure. And we also know that the interaction is not weak, so we cannot just do perturbation theory. And if we look at it, like that, a priori, it's an exponentially complex problem. So the difficulty increases exponentially with the number of electrons. It's true for lattice model as well. So the game here is to try to find approximations, methods, algorithms that will not scale exponentially and that will yield the solutions. Of course, there is a large class of systems for which we know the answer, for which we can solve the problem with an effective independent electron picture. So basically, we can do with electron in an effective potential. And there are two ways to think about that. First, on a conceptual point of view, we know that in a regular metal at low energy, the low energy theory is given, in fact, by almost quasi-independent excitations. Excitation with the charge E and spin 1/2, they're quasi-particles that interact weakly, which are renormalized compared to electron excitations. For example, the mass can be very large, so it's not a weak coupling theory, but that's basically a renormalization group fixed point description of the low energy physics. So that's almost independent electron plus corrections. In a practical term, there is also the second pillar of modern solid-state physics, which is density functional theory, based on Cohn-Hoelberg theorem, that tells you that you can solve, in practice, a problem for one electron in an effective potential, the Kohn-Sham potential, that will take into account the interaction, in average, in some sense. And from that, you can do ab initio calculations. It's used really a lot everywhere, including in the industry, and in many cases where it works very well. It doesn't display very well, but you have here, for example, the bond structure of copper. The dots are experiments, the lines are calculations, no parameter. So for simple materials, it works very well. However, the systems where we are really interested in are systems where we deviate from the standard model of solid-state physics. And by definition, these are called strongly correlated quantum systems. So these are systems where I cannot get away with a simple one electron in the potential or with a simple Fermi liquid theory. So you have many of them. In solid-state physics, of course, that's what I will discuss a little more. Typically, transition metal oxides or F electrons materials for a region that goes back to quantum chemistry and the shape of the orbitals. In nanoelectronics, for example, the quantum dots physics or the layered surfaces that you can now engineer with different kind of atoms. In ultra cold atoms, where you can engineer artificial solids of atom on light, or for example, the quantum Hall effect is another example. So let's take one example, the most famous one, which is probably the high temperature superconductors. So as people probably know, these are the families of copper oxides, cuprates, which display a superconducting temperature, which is relatively high, unusually high, compared to many other systems. And this is a sketch of the phase diagram as a function of temperature and the number of holes in the systems, which you can manipulate by doing some chemical doping. This is one example of these, the YFBCO compound. And in this phase diagram, you have a superconducting phase here as a function of doping. And away from the superconducting phase, you have a normal metal phase. But this normal metal, yes, here at very high doping will be the Fermi liquid, which I mentioned more or less before. But at low doping here, it will be a completely different kind of metal, so-called pseudogap, which means that it doesn't follow the Fermi liquid. You don't have quasi-particles in some region of the zone. Well, that's probably the biggest mystery of the cuprates, how to understand that, and how to understand how you get from that metal to the superconducting instability. And one of the key questions here is, at zero doping, this material here is an insulator. That's called a Mott insulator. And that's an insulator which is entirely due to interaction. It's a strongly correlated system. And the hope has always been for a long time that understanding what happens when you put hole in these systems is going to lead us to understand this phase diagram. So how do you do a simple picture of what a Mott insulator is? What is a Mott insulator? Okay? So if I want to draw a cartoon, I'm going to take, for example, a simple system of electrons hopping on a square lattice. That's the famous model of the field, the Hubbard model, where you have two terms. Electrons can hop from site I to J, neighboring sites, with a spin up and down. That's a creation and annihilation operator with an amplitude T. And when they are on site, for example here, they experience the Coulomb repulsion, which we imagine has been screened. There is only one number. So this model is basically a caricature of the solid, but that's what we are going to look at. And if you look at the situation where you have exactly one electron per site, meaning it's called zero doping, so in average, if the interaction is very small, well, I'm going to get a metal because I can neglect this term, so I will have a simple quadratic problem of electrons, and that's a textbook version of a metal, solid-state physics 101, half bonds. You could put 2 electrons per site, you put 1. Very nice metal. If U is very large, however, it's going to cost you a large amount of energy to put 2 electrons at the same site, like here. So you will have exactly 1 electron per site, meaning the charge motion is frozen. Electron can't move. The spin can flip, but the electron cannot move. And if the electron cannot move, you cannot have current. So you have an insulator. So that's an insulator which is entirely due to interactions. And you see what was going to be the theme of all the field in these kind of problems is the competition between these two terms. You have a kinetic energy term, you have an interaction term. This one is simple if you look at it in real space. These are independent atoms, if you want, with 4 states, so very simple atoms. This one is clearly simple if you do the Fourier transform. You create Bloch waves. And the competition between the two is what we are interested in. And in the materials, these two terms are of equal size. So we are, in fact, in an intermediate coupling problem. And that's really the point. Now, at this stage, you could ask, OK, so what happens if I take a weakly interacting problem, not strongly correlated, and in one way or another, I can reduce the kinetic energy of the electrons, slow them down, will I find this kind of thing? That's one question. The other question from the theory side is, let's solve the Hubbard model. Do I get this phase diagram? Okay, that's one of the key questions. So it happens, the answer to my first question is yes, and there is a lot of excitement in the field because very recently, new experiments appeared with graphene. Graphene is a very clean material, which is just one sheet of carbon atoms from graphene. And a priori, it's not a strongly correlated system, but if you put two layers of graphene like that on top of each other, almost in regard for each other, but slightly twisted with an angle, you will get a pattern if you look at it from above, which will have, this kind of self-repeating structure. The smaller the angle, the larger these structures are. And if you tilt them by not 4 degrees like here, but by 1 degree, very, very small, if you compute the bond structure of that without any interaction, you will find that there is a small band here of electrons with a narrow bandwidth, which means small t, which means slow electrons, to make it short, which appears in the systems. And when experimentalists do the measurements, what do they find? Well, they find Mott physics, and away from Mott physics, when you change the number of carriers, this time with a gate voltage, so it's very, very clean, you get superconductivity dome, so exactly like ITC. So there is a big hope in the field that by understanding these very clean systems and being to do experiments or calculation in it, we will be able to connect that to ITC. Yes?
It's B-wave?
We don't know, for sure. Well, the experiments have not yet been fully reproduced. As you can see, the date is very, very recent, but we don't know yet. We don't know even exactly how many bonds do I need to describe that, if it's a one-bond problem. And so because we have these uncertainties, I just show that as a motivation, but I don't want to go into these particular systems. I will stay with the standard ITC. But the problem is still the same, complete shiftation between kinetic energies and potential energy. So again, put back my Hubbard model here. So I have my two terms. So from a theoretical point of view, there are two ways to approach this problem. One is to say, there are many ways, but two ways. Let's look at the expansion around u equals 0, which we know how to solve. That, of course, gives me all the language of diagrammatics in power of the interactions. And I have all the machinery of the many-body problem, which has been designed for that. I can describe quasi-particles, Fermi-liquids. I can make more complex approximations, resummations, GW, Eliashberg techniques, many things. But I can use another language, which is the atomic limit. I can start from the atomic limit, t equals 0, because I know how to solve this problem. These are 4 states on its independent sites. And then the language which I will want to look is a language of an atom in an environment, basically addressed atoms in the language of people doing quantum optics. That's really what we want to do. And the game here is going to be, what is exactly the quantity in the many-body physics which you need to approximate by its atomic limit? So we would like to we have these two options. The question is, which one do we want to use? If you look at experiments, in fact, you want to use both. Why? Because if you look at what Mott physics is, really, the Mott physics is a story of competition between these two features I was mentioning before. A low energy feature, which is a quasi-particle peak of the Fermi liquid. This is, for example, a spectral function, as you can measure in photoemission spectrum. At low energy, you will have something which is a Fermi liquid peaks in the simplest case when it exists. And at high energy, you have the so-called Hubbard bonds, which are atomic-like excitations. They are a bit broadened because the atoms are connected to each other. And the whole story of the Mott physics is a question of transfer of spectral weight between these two structures and the competition between these two structures. As you can see also, for example, in optical conductivity here is a Mott insulator, high structure. And as soon as you introduce holes, the curve will go in this direction, create the low energy Drude peak, which will compete with the higher energy structure. And so we have this competition between these two terms, and that's not at all limited to a problem of Hubbard model, because there are more than Hubbard models, of course, in real systems. There is, in fact, a whole zoo of systems. And just to flash one thing, which I will not continue in that direction, but you can have systems with real atoms. Real atoms are not like that, right? Real atoms are more complex. They have crystal field splitting, they have Hund's coupling, they have spin orbits. There's a lot of physics which we can look at. And for example, if we take 3 orbitals, we start to be able to have terms like Hund's coupling. So what will replace the Hubbard model is a model with all these terms. Interaction between different orbitals, different spins, by density, plus some spin exchange here, which is just the Hund's term, which you know from standard atomic physics. And the fact is that for some systems, like the strontium ruthenate, for example, the physics and the correlations comes from the Hund terms, not from the Mott physics. You can be, for example, in this region, that's Z, the quasi-particle residue, in color map, so that's weakly correlated. When it's dark, when it's white, it's strongly correlated. Z is very small, and you can see you have whole region where you have strong correlation, even though you are far from the Mott transitions, because there are many of them here at different integer fillings. So the problem is not limited to the Hubbard problem. We have many systems where we need to treat the effect of the multiplets. It's even worse if you go to the lanthanide or the actinide compounds, where you have to understand the physics of the F-electron physics. Okay, but let's go back to our Hubbard model, because it's the simplest. What we want to do is to do these quantum embedded methods, and these embedded methods are approximations, generally speaking, which are formulated in terms of addressed atoms in order to have the physics of the atomic multiplets, or of U, but that can still describe well Fermi liquids and the weak coupling. So it's not just a bare atomic expansion. All right, now just to define what quantum embedded methods are. So now let me just first build it on the standard case, which we know for 25 years, which is dynamical mean field theory, and then I will use that in order to build the systems and merge it with Cyrano's paper. Okay, how to do that? So I'm going to present it in a way which is not the way which is usually used in conferences, where people talk about a mean field in the bars and so on. I want to do it dramatically. So the standard object in the many-body physics is called the Luttinger-Ward functional. So to do that, to understand that, we take the action of the Hubbard model. We add a quadratic source to the action here, so that's the bare propagator, the interaction. We can consider the free energy as a function of the source h, and the Green function is naturally the derivative of omega with respect to h. And it's a standard procedure. You can do a Legendre transform to eliminate h for g and obtain the free energy as a function of g. The Green function, you eliminate h and you get a simple term which is true at u equals 0, trace log g plus trace of g, plus a term here which contains all the difficulty, all the diagrams, which is the Luttinger-Ward functional. The derivative of that object is the self-energy, and what we want to approximate is this red object here. That, of course, we know how to write explicitly. So phi, what is phi in terms of diagrams? Phi is the sum of two particle irreducible diagrams, meaning that's vacuum. There are vacuum diagrams which I cannot cut by cutting two lines. So these ones, but not this one, because I could cut it here and here. In other words, I'm writing diagrams in terms of the full propagator. They're also called skeleton diagrams for that reason, some books. Okay. What DMFT is to say I'm going to take the approximation of phi being that of a single atom. That's where I'm going to do an atomic approximation. And that's the only approximation of the formalism. I'm going to say phi is a phi of an atomic problem with, of course, only the local Green functions, because an atom has only single site. And all the rest we can reorganize, and that will be so-called cluster corrections. So this method is exact for u equals 0, because this is 0, so clearly the approximation is fulfilled. And in the atomic limit, by definition, because then this is exact, where there is no t. So we have a method which is naturally true in both limits, atomic limit, weak interacting limit. Question is, how do we solve that approximation? Well, to do that, similar in DFT in spirit, we introduce an auxiliary problem which is precisely an atom dressed by a bar. So if I take my atom and I add a little bar of free electron in it, I have an action which looks like that, which is an interaction term, as before, single site, and a quadratic term here, which is time retarded, which is a bar corresponding to free electrons. I could write it in an Hamiltonian way if I wanted, but I can write it this way. And these are exactly the problem that Kondo, Anderson considered in the early days. Also, Cyrano in his famous paper with Philippe Nozière about the X-ray age, this kind of problem of impurity problem. But we want to use them in a slightly different context. We want to use them here as an auxiliary problem. So we have this problem, and the point is very simple, is to say that the Luttinger-Ward functional depends only on the full propagator, therefore it does not depend on the bare propagator. Therefore, the phi, the Luttinger-Ward functional of an impurity problem is independent of curl G, the bar, the bare propagator, so it is the same as the atom. So the first remark is that this approximation, because the self-energy is a derivative of phi, tells you that the self-energy is given by the self-energy of the impurity. It's a local approximation. And the second point is to say that because the Luttinger-Ward functional is exactly that of the impurity, the only thing you have to do is to adjust the bath so that your local gain function is exactly the one you will have in your lattice problem, meaning that your lattice equations, local is equal to the impurity. So if you rewrite these two equations together, this gives you an equation here, which is an equation between the local gain function of the impurity, the self-energy of the impurity. They both depend on the bath. If you solve the impurity, that's the equation for the bath. It's an implicit equation, but that's an equation for curl G. And that is DMFT formalism. So you have this atomic approximation is in practice resolved by solving an impurity problem like that with a bath, for which we have explicitly an equation, and we can compute both. So we solve both simultaneously. So that's what I want to replicate to higher order of irreducibility. But before I do that, let me note that it's very analogous to DFT, because instead of having one electron in an effective potential, what I have is one atom in an effective bath. So in some sense, it's a dual theory of DFT in that sense, loosely speaking. So as I said, it works when the atomic physics is important, so when you really need to have a solution of the atom exactly, which is very hard to reconstruct if you do simple perturbation theory. That explains why you can combine the two. This is one of the reference, for example, if you want to do ab initio calculation for strongly correlated systems, that gives you the method today, which is used to do so-called DFT plus DMFT, where you can combine the whole complexity of materials and the solution of the many-body problem in this way. Now, as I mentioned before, this method is in fact controlled because I can write, all the other terms after the atomic approximations. I can take terms which requires 2 atoms, 3 atoms in order to, solve. So these are technically called cluster methods. Instead of solving one site, I can solve 2 sites in the bath, 4 sites in the bath, or more. And clearly, if I start solving a large system, I will be going to the full solution of the lattice problem. So a priori, I have a cluster size. I have a control parameter, in theory, which is the size of the cluster. Another way to say that is that I have the momentum resolution in the self-energy. The self-energy is constant in DMFT. You can start making it constant by piece in small patches and increase resolution. These are equivalent point of views to a large degree. So we have a method which starts from atomic physics and which is controlled. Now the natural question you can ask is, well, can you converge that in an interesting regime, right? And the answer is yes, you can do that. If you look at the Hubbard model, you can see by doing the calculations that in this region here of Fermi liquids, DMFT is weakly corrected. Of course, the higher you go, the lower you go here in temperature, the closer to the interesting physical regions, the more you have cluster corrections. So can you converge? And as I said, the answer is yes. And that's a tour de force, basically, that's been done recently by my collaborator Michel Ferrero and his postdoc Wei Wu, is to push the cluster methods sufficiently well to be able to solve here, meaning in the pseudo-gap region of the Hubbard model. So in that region, we have a numerically exact solution of the Hubbard model, and we have the start of the physics of the pseudo-gaps. In the pseudo-gap, one of the characteristics of the pseudo-gap, if you look at photoemission spectra, is that you have quasi-particles in some part of the Brillouin zone and no quasi-particle in the other ones. Normally, you should see the whole Fermi surface here, but you see only an arc. It's called Fermi arcs. And the closer you go to the Mott physics, the smaller these arcs become. This you can exactly see in the exact solution in that region. So we have a solution in a non-trivial region of the models, and that's thanks to recent progress in algorithms. So we can solve that. They also solve that with a completely different method called dramatic Monte Carlo and find exactly the same answer. So you have 2 numerical techniques that then converge at that point. Now, is it enough? Well, not really, because we would like to go here, right? We would like to understand the superconducting phase. That we can do with clusters with some momentum resolution. If you go here and solve clusters without converging them up to the full momentum resolutions, because we can't solve them, we can already solve 8-site, 16-site clusters with that kind of resolution in K-space. That's, for example, these calculations, which we did with Emmanuel Gould 4 years ago. And the work of many people with small clusters, basically you can summarize by saying that all of these methods will display a similar phase diagram, meaning a pseudogap regions, Fermi arcs, D-wave superconducting dome. So clearly the question is, well, can we go beyond that? Can we really converge the solution of that? And why are we blocked with this kind of methods? And one of the things which is missing in this is the physics of large fluctuations. When you have a system like that, you can have magnon, I mean a fluctuation of spin, a fluctuation of charge that can propagate at long distance. And because these methods are very local, they cannot describe the feedback of that into the electronic fluid. That's just a fact. So we want to do that, and we want to add that, and we want to add to be able to solve systems really there at low temperature. So there where the three legs come from. So this is just, introduction to where the problem was a couple of years ago. What we want to do is to have simultaneously the physics I just described, meaning the Mott insulator, the short-range physics which we had with clusters, but we also want to have this long-range fluctuations. For example, spin fluctuation theory or charge fluctuations, which you can conveniently describe, let's say, with simple diagrams like that, self-consistent Elias-Berkeley. And we know this is also part of the physics, and we like to have a formalism that can have both simultaneously. That at weak coupling, asymptotically, will give you fluctuation physics, charge physics, and at strong coupling will give you DMFT. To unify these 2 points of view, which are two of the big point of views in high TC theory. How we do that? Well, if we look back at Cyrano's paper, in fact, there is the answer in this paper. Because the first method I described is just the two particle irreducible quantities by doing a Legendre transform with respect to the one-body Green functions. But you can continue, and that's what is constructed in this paper, by taking, for example, if you have a system with a boson and a fermion, you can do that to eliminate, to obtain a functional of the vertex lambda of interaction between the electron and the boson. You can, of course, continue and have a function of your four-leg problem. So the more you do that, the more complicated the equation that closes the systems is. Here you get the famous Parquet equations. So it's getting more complicated. However, if you do it in the middle for three particle irreducible objects, the equation is still manageable, and that's the method which we want to do. So we want to do exactly the same thing that I have done for DMFT, except I want to do it with this kind of functionals. And of course, changes everything. So the idea is that the more irreducible you are, the more local you are. So we are going to be able to converge faster and capture more physics. So to do that, you need to, of course, have a system which is in the language of an electron on a boson. So this can be any kind of system where you have electron and bosons. If you take the Hubbard model, you need to do a Hubbard-Stratonovich decoupling that will just decouple the charge and the spin with an auxiliary boson, but you can consider an electron phonon problem, or directly the electron gas by decoupling the interaction of Coulomb in the way we do in a GW method. Any kind of these systems. So you can do that for the Hubbard model. I'm going to skip the details of the equation, that does not really matter how we do that. But in terms of formalism, we have now an action with a boson, an electron, a boson, and a Yukawa type interaction between those. And we can construct the same functional as before, except now there are two copies, one for the fermion, one for the boson, and then the Luttinger-Ward functional for both of it. If I were stopping here, I would do extended DMFT. That's one of the variants of DMFT. But I don't want to stop here. I want to do one more step, which is what Cyrano did, is to take another Legendre transform to eliminate the bare coupling constant, lambda, for the three particle correlator, CC dagger phi. That's the average value of the phi field, so you can neglect it for the moment. The connected three correlator objects, or the lambda, which is the amputated version of it, the same thing. These kind of diagrams. So if you do that, you rewrite the free energy as a function of the Green functions and lambda. You have the same term as before, plus an additional term, plus a functional, a new functional, which is this time the three particle irreducible diagrams. Diagrams which are not like these, but like these. Diagrams you can't cut by cutting three legs. And now if you derive this with respect to the Green function, what you get is not the self-energy, but the vertex corrections. So the corrections to the interactions. So we want to follow the same idea, right? We take this functional, we take it in the atomic problem, because we want to capture the atomic physics exactly, and therefore we are going to replace lambda, which is a very complicated object, by something slightly simpler, which only depends on two frequencies, which is the impurity model lambda. And by constructions, I will achieve what I promised, because if the t is equal to 0 in the atomic limit, well, by construction, I will be exact. In practice, as soon as I get to a large interaction, I will recover DMFT or cluster DMFT. And at low coupling, with coupling, well, this is a vertex corrections, but I still have a vertex, which is a bare vertex. So I will get basically the spin fluctuation diagrams or any Eliashberg theory I started from. So by construction, this method will exactly fulfill what I wanted. Have long-range physics plus local Mott physics in the same formalism. The key question, which I'm not going to explain, is how do you solve that, and can you solve that with an impurity model, because it's good to write an approximation, it's better to solve it. So there is a construction here, which I have no time to explain here, that shows that in fact you can do that, and I'm just flashing you and giving you the final equations of Trilex, which is the following. You solve a self-consistent impurity problem here, the same as before, except now the interaction is becoming retarded. That's a new difficulty. It's not just the same interaction in the bare model, you have retarded interactions. From that, you compute the vertex calculations from the impurity. You inject that into the equation for the self-energy, Eliashberg-like. So these ones, plus the local vertex, and you have the self-consistency conditions, which I will not write in detail, it's too big, but which does this and compute the bar here and the retarded interaction. So you have an impurity model with the retarded interactions. And in fact, we are lucky, because for the last 20 years, people have worked a lot on how to solve these models, and it happens that we also found a way to solve problems with retarded interactions. And for single-site problem, we have algorithms, continuous time quantum Monte Carlo, which are sign-free, meaning we can solve them in polynomial time, not exponential time. So we can solve that with all the toolbox of DMFT, except we have a completely different method, because we compute something different.
That you have in this manipulation, you have the sign problem has disappeared?
Because I have a single site. At single site, sign problem disappears. As soon as I put more cluster, it reappears. The question is, do you converge before the sign problem kills you? Because we know the bars improve the sign problems in all of these methods. So we want to do more physics with a simpler site, instead of having larger and larger cluster to do it. So that's exactly the reason why you want to do it with more. You want to do more with an atom, because that you know how to solve. All right, so now I want just to flash two results for these methods. The first one is really that the field of many-body physics has changed a lot in the recent years, even though it may not be obvious for people who are not in it. And one of the reasons is the Simon's many electron collaborations, where people started to have systematic benchmarks of different methods, which, and Julius has worked with me on this field, was not the standard before, and how exactly you do, very serious benchmarking between these different methods. So now when you introduce a new method, well, the first things people ask you to do is to benchmark them with the Simon's collaboration benchmark. So that's what we started to do. And how you do that, well, is you need to have the control, which I mentioned before. You need to do clusters, meaning one side, two sides, three sides. So can you do cluster Trilex these times, and not cluster DMFT? Yes, you can. These are the equations. I'm not going to explain them in detail, but just to show them. You can coarse grain the vertex on these little patches. This looks impressive, but in fact, it's very simple. It's just a coarse graining of these different patches with different resolutions, and you end up with a multi-orbital solution here, multi-patch solutions of your system. So you can write cluster, smaller clusters. And it turns out that we can also solve them. So that's what we did in this paper with Thomas et al. For the first four at least. Again, with improving the algorithm which we had to solve previously, and then we can benchmark this. So I'm sorry here the curve is a bit busy, but let's look only at these two panels here, where we have the solution of Trilex in the regime of the benchmark, so relatively high temperature in the Hubbard model, for one side, two sides, and four sides. So, and the star are the benchmarks, meaning very large, very demanding DMFT calculations, which takes, really supercomputing capabilities to do. And you see that with a relatively cheap method here, you have a very good K resolution of the self-energy, that the real part of the self-energy is the first Matsuburg frequency, the imaginary part, and you are very close already to the benchmark when you're very, with a single, not a single site, but with a four-site Trilex. The other thing is, all of these methods with a decoupling are usually plagued with an ambiguity, because you need to choose in which channel you're going to decouple, and then you do a mean field. What we have shown here is that we can use this to our advantage and show that when the calculation has converged, of course, the ambiguity, disappears, and you can use that as a check to check the convergence of clusters without going to larger clusters. And when we solve the systems where we do not depend on exactly how we decouple with the bosonic channel, then we have converged and we are on top of the benchmark. So this method has been benchmarked, at least on the existing benchmark which we have in these Hubbard models. And since my time is almost up, I just wanted to show two results. One, we can study again the Mott transition with this kind of technique as a function of U at half filling, and to check explicitly that indeed at weak coupling we are going to find a metal where you have spin fluctuation physics. We knew that here spin fluctuation is exact, and at high coupling we have an insulator, the Mott insulator. We are exactly on top of the DMFT solution as we expected, and in the middle we have a metal where we have corrections, we have K-dependent self-energies, which we couldn't capture with the methods before. Okay? And that is there. If you start doping that, you will get Fermi arcs, you will have the metal which we are looking for the pseudogap. Now, that's for the normal phase. For example, here you can see the self-energy that depends a lot of K. That's exactly the spin fluctuation physics if you solve spin fluctuations. And here you have almost a flat solution independent of K. That's the DMFT solution. So you can interpolate between the two explicitly, not only in theory, but in practice. And you can solve the calculations. Now, the last question is, do we find superconductivity? It's an interesting question. Answer is yes. Again, look only at the red curve here. The other one are other comparisons with other more primitive techniques. What you find here as a function of temperature and doping, so that's exactly the phase diagram of high TC. For the Hubbard model, you have a dome of superconducting solutions, D-wave, with a single site impurity problem, because you can get the superconductivity with the Liège-Berg aspects of the solutions, and you have the Mott physics that give you exactly a dome. So, of course, we need to refine this and to larger clusters at lower temperature, which is something which is, of course, work in progress. But you have the bare element, again, with a method which is more compact, converge faster than the previous methods. So, just to summarize, the point is that by putting these ideas of higher irreducible functionals and the basic idea of DMFT, in fact, you get a family of methods, and DMFT is just the first of these methods, which you can solve. The other one's called quadrilex, T-gamma 8. There is a whole industry of people working now. Where you have long-range fluctuations and also local Mott physics, which what we wanted to do for a long time. One of the results which we already have in that the pseudogap of the Hubbard model, we need clustering Trilex, meaning short local Mott physics plus long-range fluctuation is not enough to describe the physics. You really need the bonds, the first neighboring correlations, short-range correlations, LIRVB if you want. A point which I didn't want to discuss here is that this is all fine, but this is just the surface, because what matters is the algorithms to solve these things. That's 99% of the problem, on which we made a lot of progress in the recent 10 years. Every 2 years, we can have orders of magnitude improvement to solve this, so which allow precisely to solve the equations I presented. And there are, of course, many directions, because there are systems which we know have long-range physics, in fact, probably more than the high TC, but there are multi-bands, like the other superconductors discovered in 2008, pnictides, which have been described in terms of these. The electron gas directly, it's a big problem. We want to go beyond the GW plus DMFT technique, just to have ab initio calculation of the electron gas, or electron phonon problem, for which it's a very natural language. And that, I think my time is up. So thank you for your attention.
in the impurity action for 3-dex, why you don't have a dynamical vertex?
You do. Okay, that's a very good question. In practice, you do. Normally, you should write it in terms of electrons and phonon, and have a dynamical vertex that should depend on 2 times to close the equations. It just happens that for the regime where we were, this renormalization of this dynamical bar for the vertex is small, so we could neglect it interacting, and then we can solve it in this simpler. And the second part of the answer is that this was fortunate because until recently we didn't know how to solve impurity problem with this dynamical vertex, and now we do, so we can certainly see whether there are corrections for that. But in the result I presented, fortunately, it's small, which is related to the fact, we could discuss later, but that this equation, where is this equation? Where is my equation? Yes, this equation here, which is the analogous of the Dyson equation, is related to the derivative of the function of this equation, remarkably is linear. While the Dyson equation for the 2pi is nonlinear, and for 4pi is even worse, that's Parquet equation. So 3pi, the equation here is remarkably simple, and that yields simplifications like this one, to a large extent.
Other questions? I see none. So thank you again.